Welcome to the Deep Dive, where we take a massive stack of articles, research, and declassified files, and, well, we extract the absolute core of what you need to know.
Today, we are strapping in for a deep dive into an incident that, even now, 60-some years later, remains one of the most terrifying non-detonations in history.
We're talking about the 1961 Goldsboro B-52 crash.
Exactly. This incident is famous, or maybe infamous, because it perfectly illustrates how everything can go wrong. You have organizational complexity, mechanical failure, and safety protocols that just weren't quite up to snuff.
And they all nearly collided with, truly catastrophic results. We're dissecting the declassified records around a Broken Arrow incident.
That's right. It took place near Goldsboro, North Carolina, on January 24th, 1961.
Okay, so let's unpack this for a moment. A Boeing B-52 Stratofortress, part of the Strategic Air Command's coverall mission.
So a 247 airborne alert.
Right. It broke up midair carrying two enormous 3.8 megaton Mark 39 thermonuclear bombs.
And just for context, 3.8 megatons is hundreds of times more powerful than the weapon dropped on Hiroshima. It's almost unfathomable.
So our mission today is to see exactly how close this came to becoming a disaster that could have, well, contaminated the entire eastern seaboard.
The Goldsboro accident is rightly considered the most critical Broken Arrow incident. And what makes this so chilling, according to the internal analysis that was later declassified, is the consensus that one bomb was literally one final safety switch away from detonation.
One switch.
It's a miracle of simple mechanics that saved millions.
And before we get into the engineering, we should acknowledge the human cost.
Mm-hmm.
There were 8 crew members on that B-52G.
5 managed to bail out, but 3 were lost.
1 ejected successfully but died on landing, a TSGD Francis Barnish, and 2 others were killed instantly in the breakup itself. They were flying a routine mission that just turned into a deadly emergency.
Absolutely. The crew were part of a continuous airborne alert. This was SAC's way of ensuring a nuclear response could be launched, even if U.S. ground bases were hit first.
So let's set the scene for the flight itself. The B-52G takes off from Seymour Johnson Air Force Base. The critical issue starts around midnight.
Right, during a rendezvous with a KC-135 tanker for aerial refueling. Totally standard practice to extend their loiter time.
But something goes wrong.
It was the tanker crew that spotted the trouble. They noticed a severe fuel leak just streaming from the B-52's right wing.
Now, you said fuel leaks weren't totally unheard of in these planes. The wet wings?
No, not unheard of. But this was different. The problem escalated incredibly rapidly.
So they aborted the refueling.
Immediately. The plane was directed to hold off the post, to burn off fuel and reduce weight for an emergency landing. But the pilot reported an extreme leak rate.
The numbers in the source material are just staggering.
They are. 37,000 pounds of jet fuel lost in just 3 minutes. That's nearly 6,000 gallons. The structural failure was, at that point, inevitable.
Even if the pilots didn't know it yet.
Correct. They were ordered to return to Seymour Johnson immediately, but as they began their descent through 10,000 feet, the wing's structural integrity just failed, catastrophically.
And they didn't just lose altitude, they lost all control. The pilots described it as a violent, uncontrolled spin.
A gyration was the term they used. The pilot, Major Walter Tulloch, ordered the crew to bail out at 9,000 feet.
And it's important to note the plane was still basically intact at this point.
Yes, which means both nuclear bombs were still secured inside the bomb bay when the crew ejected.
That decision saved 5 lives. But we have to pause here for this remarkable human detail about one of the co-pilots, LT and Adam Maddox.
It's an incredible story. His ejection seat malfunctioned. He is the only known person to have successfully bailed out of the top hatch of a B-52 without an ejection seat.
How was that even possible?
He somehow navigated around the tail fin and through the hole left by another seat's departure. Just an amazing feat of survival.
So, shortly after the last man gets out, the pilotless aircraft just breaks up violently, wreckage scattered across 2 square miles of farmland.
And witnesses on the ground reported seeing 2 flashes of red light, probably fuel explosions as the final event in that breakup sequence.
And this is where the story shifts from a tragic aircraft failure to a potential nuclear catastrophe.
Because when that B-52 broke apart, the 2 Mark 39 bombs were released into the night sky and they began their own terrifying arming sequences.
Okay, so to really understand the severity here, we have to look at the weapon itself. the Mark 39 Mod 2.
It's a multi-stage thermonuclear bomb. You have a fission primary that acts as a trigger, and then the fusion secondary. A massive, massive weapon.
So walk us through, step by step, the redundancy system that was supposed to make sure this bomb can only fire on command.
Absolutely. The whole sequence was designed to need, well, 5 highly specific sequential actions, a mix of human input and electromechanical automation.
Let's start with the manual controls. What did the crew have to do?
Okay, so the first, most basic barrier was the crew manually pulling what are called safing pins with a lanyard. These pins physically restrained the arming rods that start the whole sequence.
After that, it's up to the pilot.
Up in the cockpit, yes. The pilot had to deliberately flip the T-380 readiness switch. That switch enables the next step, the T-249 aircraft monitor and control unit.
So we have the human element pins and a switch setting the stage. What happens when the weapon is actually released?
That T-249 control unit then operates the crucial MC-722 arm-safe switch inside the bomb, and this is the key component.
The arm-safe switch.
Yes, and it was a low-voltage, solenoid-operated device. It only needed a standard 28 volts DC to move from safe to arm.
Wait, hold on. Only 28 volts? To move the most crucial safety switch? I mean, given the violence of a midair breakup, an electrical short seems almost guaranteed.
That's the core vulnerability. That's what the sources uncover. They relied on that electrical current because the whole system demanded it. Once the bomb separated and the arming rods were pulled out by the force of the fall,
It becomes automated.
completely. A small internal generator called the Bish generator would fire. That starts the MC-543 timer, set for a 42-second countdown.
What does that 42 seconds buy them?
That's the time needed for the high-voltage thermal battery to activate and charge the X unit. The X unit is the final firing set.
So the bomb can only detonate after that timer completes its countdown.
And the X unit is fully charged. Then, the absolute last physical event needed is the MC-616 crush switch on the nose, closing on impact.
It sounds like a pretty solid chain of redundancy, at least on paper.
On paper, yes. But here's the critical context our sources reveal. A major safety modification, designated Alt-197, had been approved to fix a known vulnerability.
But it wasn't installed on these particular weapons.
Exactly. That's the organizational failure behind the technical one. Alt-197 was designed to add an essential mechanical layer of protection. It would have made it impossible for the low-voltage battery to charge if the arm-safe switch was left in the safe position.
So without that modification, the whole system was vulnerable to a stray electrical signal, even if the crew did everything right.
Precisely. It's a disastrous combination of logistics and resource allocation. These weapons modifications take time, and they were flying with an older version of the Mark 39. This missing Alt-197 is the ghost in the machine that allows what happened next.
Let's focus now on weapon number 1, the one in the aft bomb bay. This is the one that nearly ended everything.
It was found a mile from the main wreckage, standing nose up in the dirt. Its parachute had deployed.
And its arming sequence.
The details are deeply unsettling. It shows that those safing pins were, well, functionally useless. As the bomb twisted violently from its rack, it just pulled the pins right out.
So the automatic sequence began.
Instantly. The arming rods withdrew, parachute deployed, Bish generator fired, low-voltage battery actuated, everything.
And critically, the 42-second timer, did it run its full course?
It ran its full length, which allowed the high-voltage battery to fully charge the X unit. And upon impact, the crush switch on the nose closed. Every single requirement for a thermonuclear blast was met.
Except for one.
Except for one.
What stopped it? What stood between the United States and utter disaster?
The saving grace was that single component we discussed, the MC-722 arm-safe switch. When the EOD team got to it, they found that despite all the violence, all the electrical chaos,
it had held.
It had held in the safe position. It prevented that final circuit from closing and firing the primary stage.
It's an almost absurd irony. This hugely complex, multi-stage weapon, the cutting edge of Cold War science, was stopped by a low-tech solenoid switch.
That's precisely the controversy that was summarized by a Sandia supervisor, Parker F. Jones, in 1969. His famous conclusion was that one simple dynamo technology, low-voltage switch stood between the United States and a major catastrophe.
And the margin was razor thin. Why so thin, specifically?
Because Jones and other engineers had already documented about 30 previous incidents where that exact same type of switch had been inadvertently flipped by stray 28-volt currents.
The exact kind of electrical short you'd expect to happen during the violent breakup of an aircraft.
It's almost guaranteed. which means that if any wire had shorted out during the fall, just for a moment, and applied 28 volts to that line,
the switch would have flipped to arm, and the bomb would have detonated upon impact.
with full nuclear yield. The reliance on sheer luck rather than mechanical impossibility became the defining takeaway of the Goldsboro incident.
But the story doesn't end there. If weapon number 1 taught us about a single point of failure, weapon number 2, it presented a completely different but just as terrifying scenario.
Indeed. Weapon number 2, from the forward bomb bay, separated at a much lower altitude. We're talking maybe 2,000 to 5,000 feet. And its parachute failed to deploy at all.
So it was just in a high-speed, uncontrolled freefall.
Estimated at 700 miles per hour, it plunged deep into the earth.
Did its arming sequence start, like the first one?
Yes, its safety systems also began to arm. The saking rods pulled, the Bish generator fired, the low-voltage battery actuated. But because it hit the ground so quickly,
The timer?
the timer had only run for an estimated 12 to 15 seconds.
So in this massive twist of fate, the incredible speed and violence of the impact was actually what saved it.
Precisely. The timing failure, not a switch, not a pin, prevented the blast. That short duration wasn't enough time for the high-voltage battery to fully charge the X unit. The firing circuit just wasn't ready.
But there was another immediate scare for the EOD teams on the ground.
Oh, the tension was immense. It took them days to excavate the debris, which was buried deep in freezing mud. And when they finally located the MC-772 arm-safe switch from this second bomb,
What did they find?
they saw that the indicator drum was visually rotated to the arm position.
Oh, wow. So the officers on the scene must have believed they were dealing with a nuclear dud that was fully armed.
That was the immediate, terrifying conclusion. But later analysis determined the sheer force of that 700-mile-per-hour impact had been so great that the bomb broke apart. It sheared the switch away, electrically disconnecting it. It couldn't have closed the circuit.
The impact itself destroyed the wiring.
Exactly. The excavation effort was, it was a Herculean task.
Right.
They managed to recover the heavy primary stage, the fission trigger, at about 20 feet deep.
But they ran into problems.
A severe water table and just extreme mud. After weeks of effort, digging down to 42 feet, the Air Force made a consequential decision.
Which was?
They officially abandoned the effort. The Air Force determined that continued recovery operations are not economical feasible.
And the critical legacy of that is that the thermonuclear secondary component of weapon number 2 was never recovered.
It is still there. Later geophysical surveys estimated its depth at around 180 feet, plus or minus 10 feet. It is still buried in that field.
So what does this entire sequence of failures, from the leaking fuel line to the faulty pins, actually mean for military policy? This deep dive revealed some severe consequences.
The policy change was immediate and absolute. After the accident, the military redlined all other Mark 39 Mod 2 weapons that were missing that critical Alt-197 safety modification.
He took them off deployment.
Until the new, mechanically superior MC-1288 arm-safe switch could be installed, it directly influenced future safety programs, shifting the focus toward mechanical reliability, away from things that could be fooled by stray electricity.
And this must have also put a huge amount of scrutiny on the B-52 fleet itself.
Absolutely. The structural failure highlighted major stress issues in the B-52G's wet wings. It led to significant modifications starting in 1964. They fixed the aircraft because the source of the crash was a design failure under stress.
And the public disclosure really cemented the gravity of this. Secretary of Defense Robert McNamara confirmed it in 1963.
He did. He said a nuclear explosion was averted by the slightest margin of chance, literally the failure of 2 wires to cross. That statement crystallized the danger for everyone.
That confirmation turned institutional knowledge into public record, and the local area remains marked by this history.
It does. In 1962, the government purchased a perpetual 200-foot radius circular easement over the remains of the second bomb.
And the terms of that are very specific, aren't they? It prohibits digging below 5 feet and restricts the land to just farming.
That's right. The intention is to leave the device undisturbed forever. Periodic state groundwater tests, which are still conducted today, have revealed no contamination from the components.
And in 2012, the state of North Carolina put up a historical road marker. It calls the event simply a nuclear mishap, a permanent visible scar in the landscape for an invisible hazard buried deep below.
We followed this terrifying sequence. The plane falling apart, the weakness of the saving pins, the arming sequence initiating, only to find that simple mechanics and just pure dumb luck were the final bulwarks.
The Goldsboro incident really forces us to confront the inherent complexity and risk of these airborne nuclear alert programs. It is a textbook case study.
It shows that safety is never guaranteed, and often it's the cumulative failure of redundant systems rather than one single mistake that defines a true near miss.
We hope this deep dive provided you, the learner, with the context and the critical declassified details of this remarkable and nearly tragic event.
It really does illustrate the fine line humanity walked during the peak of the Cold War.
So a final provocative thought for you to explore. Does the knowledge that a 3.8 megaton warhead component has permanently sealed 180 feet below North Carolina farmland, defined only by an easement preventing digging, fundamentally change how we view the safety and the history of the ground beneath our feet?
Thanks for diving deep with us.